Now, if we look at all the stars that we've seen in our galaxy and around the universe, what we can actually do is we can start to plot them on a graph that looks a bit like this. Now, on the y-axis, what we have is their luminosity. Now, the luminosity is basically how much light they give out. And what we tend to do is we tend to compare everything to the sun that we have in our solar system, because that's like a sort of standard thing that we compare things against. So say we have the kind of standard luminosity of our sun, and we say that's just got a luminosity of 1. We can look at things which are much, much brighter and much, much dimmer. But because in the universe there's such a spread of brightnesses and I guess things which are quite dim, what we can actually use is a kind of logarithmic scale. So effectively we'd have like a value of 1, something which is 10 times brighter, 100 times brighter, 1,000 times brighter, and so on. So this isn't a linear scale, but it's actually a logarithmic scale. So we can look at the luminosity up on the y-axis. Now the other thing that we can look at is the temperature of the star. And effectively what we have is actually the temperature doesn't go from left to right, it goes from sort of right to left. So we start out with things which are fairly cool, and I sort of say relatively cool. This is about maybe sort of 3,000 Kelvin. We can then sort of move up to things which are maybe sort of 6,000 Kelvin, up to maybe really hot stars which are maybe 40,000 Kelvin. And this is the temperature at the surface of the star. In the actual core itself, it's incredibly hot. But again, we have a whole range of temperatures, and what we have is this kind of sort of logarithmic scale on the x-axis. And what we find is that our star sort of sits sort of somewhere in the middle, a bit like this. It's about 5,000 Kelvin or 5,000 degrees on the surface, and it's got a luminosity of 1. But when we actually start to look at other stars which are in our solar system, we tend to find that they're sort of a bit like this. So what we find is that some of them are a lot brighter and a lot hotter, and some are a lot cooler and a lot less bright. You know, no big surprises there. And what we find is that most stars tend to fit onto a sequence that looks a bit like this. This is where sort of 90–95% of the stars tend to fit. They tend to sit on this sequence over here. But what we do have is occasionally we have stars which are quite cool on the surface, but they give out a lot of light. And so therefore their luminosity is really high, but yet their surface temperature is actually relatively cool. We also have some stars which are incredibly brighter than they're incredibly hot, but they don't give out a huge amount of light, and they sort of sit down here. And this thing here is what we call the Hertzsprung Russell diagram. And this is sometimes shortened to just the HR diagram. And it's really useful because it basically not only kind of shows where most stars are, but we can actually look at this in terms of the evolution of the star. We can actually track the progress of maybe a normal kind of star like our sun, until it becomes maybe a red giant, and then at the end of the life it becomes a white dwarf. And what we can see is that we have different regions. This region here is again called the main sequence. We have red giants, and we also have white dwarfs. If we were to track one of these stars over its lifetime, what we'd see is that a low mass star moves from the main sequence up to the point where it's a red giant, and then it moves down to be a white dwarf, and we can sort of track it on a diagram like this. If, however, you have a high mass star, these are the ones which burn incredibly brightly, and they kind of give out this sort of whitish, kind of almost like blue light. And therefore we can sort of maybe track the life cycle of one of these high mass stars. And what it does is basically it ends up kind of sort of moving over here to the region where it's giving out a huge amount of light, but it's not particularly hot on the surface. And then at this point it then disappears from the diagram, and that's when it explodes in something like a supernova, or that's when it kind of then will then disappear maybe into a neutron star or something like a black hole. So this diagram here is a really useful way to actually visualize the life of a star.